let me give a plug here. Well, for all of you might be interested, but I think especially people in electrical engineering and computer science might be interested in today's math club, 5 o'clock, right over here in Martin M102. It's actually about how you use mathematics to do security on computers and also error correcting. So I think that might float your boat. Roll on by, math and peace. Okay, so right. Let me give you kind of a funny piece of general. This will be kind of a nice segue. I'm gonna bleed over some of the stuff we were doing last time to do this next section here. I'm going to go through this. But I set this matrix up in a very kind of simple way. Let me ask you a question. You know, I always said, and I just made this up off the top of my head, right? So I get a little nervous and following sense. What if I accidentally made up a singular matrix, right? Won't I be embarrassed? But I know I didn't. Can anybody tell me how I know that this one is inverted? Yes. Or yes.
There's new data in every
I'm sorry.
there's a pivot in every column, none of the rows are on schools.
That's right. So that's a big fat clue, isn't it? Right? She said there's a pivot in every column, and she's right. So that means that we should be able to reduce this to the identity matrix, which means, according to, I believe what I said yesterday, you need to figure out the inverse. So let's kind of go through it. Yes.
You bring this.
Is this? Yes. Sorry about that. That doable now? So let's do this thing. Let's see. I'm going to put the identity matrix up here. 0 times 1 times 3. Now, here's the procedure. If you remember, what did I do? I took this thing over here on the left and I tried to reduce this to the identity matrix, and then it does some stuff to this. When I'm done to get the identity matrix over here, I should have the inverse neatly waiting on it, right? So I think the first thing to do is I'm going to take this one here and I'm just going to nuke everything above it, right? So I'm going to have this still on the bottom. Let's see. This is going to be 0, 0, 1, 0. I'm going to multiply that by -2.5 up here. And the same thing here, 0, 0, 1, minus 2. Right. I'm going to multiply this by -3 and take this out. Multiply that by -3 and I get 0, 1, 0, minus 3. And finally, I'm going to multiply this by -4, take this out. And by -4. Now, what I'm going to do here, just to make my life easier, so reverse the sign of that second row, right? Now I'm going to take this, my -1, and take this out. 0, 0, 0, 1. This is going to stay with be stable 2, 0, 0, 1, 0. 0, 0, 1, 2. Okay, I'm going to use this to take this out. So I'm going to multiply this by -1 and that here. 0, 1, 0, 0. So we're going to multiply it by -1 here. Here, so I'm going to have -1, -1, 5. I think that's right. Right, rule supply. And now it looks like there's only one thing left, and that is get this last 2 out of my hair.
How did you get 5?
I'm sorry?
How did you get 5?
Because what I did is I multiplied this row by -1 to get this. So that's going to be -2 plus 3 is 5. And so finally, let's see. For the bottom, here go 0, -1, -1, 5. 0, 0, 1, 1, 2. 0, 0, 0, 1, 1, 2. Finally, multiply this by -2 and add it here. 1, 0, 0, 0. Multiply this by -2 and add it up here. So I'm going to get 1. I'm making 2, 2, making 2, 2, making 2. That's -2. So the inverse of the original matrix could be this. Everybody okay with that? Okay. Any observations? I like your first observation that, okay, I know that this is going to work because there's a pivot in every column, right? Yes.
Still in row echelon form.
Right, it is in a row echelon. It's not reduced, but it's a row echelon. Yes.
The diagonal.
Yeah, in this particular case, the diagonal entry is the same, but notice that this is what we call an upper triangular matrix, right? And you guys see why, right? Because everything of significance is on the diagonal or above. So upper triangular, right? All zeros below the diagonal. Notice its inverse is also an upper triangle, right? In general, when matrices aren't upper triangle, it can be kind of a mess, but you know, this is what we get here. So that's kind of a nice observation to make. Let me ask you this: if you believe or think about pivots, which is true, suppose I walk up to you on the street and give you an upper triangular matrix. Can you give me a quick way that you can just put your eyeballs on that and tell me yes, it's invertible or no, it's not? Yeah.
Well,
Okay, right. So if it's upper triangular like this, look at the diagonal. What do we need? A pivot. We need in every column to be a pivot column. What's a quick way to tell? Just by looking at the diagonal entries. They all have to be not zero, right? If any of those diagonal entries are 0, you're totally hosed and there's not enough pivots, right? Okay, let me ask you this. I asked you this last time. Okay, we've learned a little arcane mathematical prestidigitation here, right? Why does this work? Right? Mathematics isn't just about doing, it's about knowing. Why does this work? Yes.
Well, if you multiply a matrix by the inverse, you're going to get together.
Okay, that's good. So here's why this works. What you're doing every time, and I'm going to do kind of a 3x3 example just to make it easy. This works. What did I do in my sequence of steps? I did row operations, right? And our old row operations. And actually I only used two of them because my matrix was up triangular. I never had to swap any rows, right? So what did I do? I used multiples of one row and added it to another, right? And in one case, I changed the sign of this row. So I multiplied a row by a non-zero. So let me just give you some 3x3 examples. What would this do to a 3x3 matrix?
Or multiply A by 5.
It would multiply what by 5?
A,
And not only that,
but
It will-
also against.
this actually multiplies top row by 5. It leaves the other two rows alone, doesn't it? What do you suppose it would be if I had the 1 there and the 5 there? What would it be doing? I'd multiply the middle row by 5. It's so, right? Let me ask you a question. Is that matrix, the 5 0 0 0 1 0 0 0 1, is that invertible? Sure it is, right? Because it's an upper triangular and it has no zeros on the diagonal. In fact, I can tell you what, can anybody quickly tell me what the inverse of this is? Go again. What's that? The matrix with all zeros except 1/5, 1 1, right? Because remember, all our row operations are undoable, right? If this matrix multiplies the top row by 5, how would I undo that? I multiply the top row by 1/5, and so I get the matrix 1/5, and then the ones on the top. Everybody okay with that? Okay, what else? What else do we have going on with this? Well, let me ask you this one for a 3x3 matrix. And again, this is generalizable in by n, but I just you have to see the example. What does this matrix do to this? Anybody know? Yeah,
I would add 17 times 5.
that is correct. This one takes 17 times bottom and adds to top. Because look what happens here. This row times this column, you've got A and then 17G. This row times this column, B plus 17A. This row times this column, C plus 17I. So effectively, I've taken that bottom row times 17 and added it up there, right? And everything else is left alone. This times this, it just reproduces DEF, and then this reproduces GHI. But how about this matrix? What does this mean to? I'm kind of running out of room here. A, B, C, D, E, F, G, H, I. What does this do?
Plus the entries on the second row, and then that's or it multiplies the entries on the first row, or the first entries in all of, or yeah, the first row. Multiplies those and then adds this.
Multiplies by what?
There.
Right. This one, if you look at this, it will leave the first, the top row alone, right? So you'll get ABC. This one is going to be -4 times this row plus the middle row. So it's at, you take -4 times the top and add it to the middle, right? And then it leaves the bottom row alone. Yes.
Wouldn't it be 1 to 4?
What's up?
When you multiply by positive four,
No, -4. -4A.
will they like get,
Well, let's multiply that.
oh,
So this would be, this represents, I get A, B, C on the top. And then I get -4A plus D. -4B plus E. And -4C plus F. And then the bottom row is the same. So I took -4 times the top and added it to the middle. Do I agree with that? Are these two matrices invertible? Again, you've got a pivot in every row. Everybody agree with that? This one might, it's pretty easy to see this one's got a pivot in every, or I'm sorry, pivot in every column. And this one, all you have to do is multiply this by 4 and add it here, and you've got the identity matrix, right? So, row operation 1, invertible. This type of row operation where you take a multiple of a row and add to another row, also invertible. What's the row operation that I haven't done yet? What's the third kind of row operation? You can swap out rows. And those, in a certain sense, they look a little wonky, but in a certain sense, they're kind of easy. Can anybody describe what this matrix does? What is this? Yes.
it just switches to the middle and the bottom.
That is correct. What this will do is this will give me the same top row, but now this gives the bottom row here, promotes it to the middle, and this last one demotes the middle to the bottom. So this swaps rows 2 and 3. This is called a permutation matrix. How many of you have heard the word permutation before? Right? You might have heard it in probability class or a number of other places. So permutation just means you take a bunch of garbage and swap it out. Right? So, and what do we do? I mean, really, this is just the identity matrix if we swap the second and third rows, right? Is this matrix invertible? Yes, because I can do a very easy row operation on it. It's clearly got 3 pivots. Everybody agree with that? So here's the thing. Every single one of our row operations is reversible. Once you do it, you can undo it. If you multiply a row by a non-zero number, you can invert that. If you swap 2 rows, you can invert that. If you take a multiple, by the way, how would you undo this? Right? What did we do? We took -4 times the top and added it here. Yes. Right. To undo what you've done here, just take 4 times the top row and add it to the middle, and you're back to where you started. Right, okay? So these types of matrices so things that look like A. And I can put the A anywhere on the diagonal, but I'll just do one example. Or and here the A can occupy any of these empty 0 things. Or a permutation matrix like this are called elementary matrices. And again, you can do this for n by n matrices. It doesn't have to be 3 by 3. And they are invertible. And so now we've kind of come to a point where, listen, here's what's going on. When we first talked about these elementary row operations, I just said, okay, look, here's something we can do. We call these elementary row operations. This is a more sophisticated and useful way to see it. This is actually what you're doing when you do one of these row operations, is you're multiplying by an elementary matrix. Okay. Now, I've now come full circle. Why does that little thing that we did to find the identity or to find the inverse work? Here's why. So what did we do? We started doing these little row operation things on A, correct? We did it, we did it, we did it, we get the identity. So we started with A, and then maybe we did E1, E2, and we did it a whole bunch of times until we got the identity. Everybody agree with that? So row operation 1, row operation 2, all the way to however many times we have to do it, or row operation n. Agreed? We do that, and it turns into the identity. Now it's very simple. Multiply on the right by A inverse. And so I get En minus 1, E2, E1, A inverse is equal to In A inverse. Now, what is A inverse? It is the identity. And of course, the identity times A inverse is just A inverse. So this equation now becomes En minus 1, E2, E1, I inverse. Is equal to A inverse. And again, it's speaking to me. It's speaking the equation and speaking again, because what it says here, what this is actually telling me is if I take the identity matrix and do the same stinking row operations that I did to A, it will turn the identity into A inverse. And that is why that works. Everybody okay with that? Are y'all comfortable with the procedure of actually going through it and figuring out what you put? Okay, any questions? Okay, so let me give you a theorem in 12 parts. You guys are going to help. And this theorem is not just there to be obnoxious, although it does delight in that a bit. It is actually a number of equivalent ways, a lot of toolboxes, or a lot of tools in the toolbox to figure out something that's perfect. So, theorem. So let me emphasize that since it's an n by n matrix, it's square. Remember, we can only talk about invertibility for square matrices. All these conditions are equivalent. So if one of these conditions is false, they're all false. If one of them is true, they're all true. Number one, A is number two. And we have this from yesterday. If it's invertible, when you run this little algorithm here, you should be able to get the identity. A is row equivalent. To the identity matrix I have. How many pivots does the n by n identity have? N pivots, right? And when you do row equivalents, the number of pivots do not change. So another way to put this is A has n pivots. If you have every column is a pivot column, what can you say about the solution to the homogeneous equation? Yes, that's right. AX equals 0 has a unique solution. So there's only one solution to the homogeneous equation. That's another way to put the matrix being invertible. Anybody remember what's equivalent to AX equals 0 having only the trivial solution? What can you say about the columns today? Yes,
They're all linearly independent.
very good. Columns today are linearly independent. Let's throw in something about linear transformation, one of my favorites, right? Suppose you have the linear transformation, Tx is A times X, right? If the columns of A are linearly independent, what can you say about this?
Oh,
Yeah.
It's gonna be 1-to-1, right?
Very good. It is 1-to-1. And of course, that's the same as this equation having a unique solution as well. Okay, so AX equals B has a solution. Will all be and in fact, I could have said it's actually not only does it have a solution that's unique, right? Why is this? Because remember, A has n pivots, right? So every row contains a pivot element. And so therefore, that means that the columns of A span Rn. And so this always has a solution. And here's the next one. The columns of A span. That is to say, every possible vector in Rn you can ever make up in your head is a linear combination of the columns of the matrix. Let's go back to the linear transformation. So if the columns span all of Rn, what can you say about this transformation now? We already know it's 1-to-1. It's also on. Nobody in Rn is lonely because the columns are spanned by the matrix. There is a C in R n by n, so another matrix here. such that C times A is IN. And 12, I'm sorry, that would be 11. There is a matrix D and R n by n such that AD is IN. And finally, a transpose. Okay, so let me make a remark or two about this last bit. You might wonder about, we were kind of going to the theme here. This might seem silly, right? But can you tell me what's the difference? Because we started off with A as invertible. But what does it mean to A to be invertible? It means there's another matrix B, the same size as AB and BA equal the identity. What is really Tim saying there? Yes.
There's an invertible.
Right, and we only have to test it from one side. Right? So what this says is if there's a matrix that hits this on the left and makes the identity, there also must be a matrix that hits it on the right. So when you have that it's invertible, you don't have to put that part in the definition. Yes.
I was gonna say that C can represent a linear combination that can make A equal to the identity matrix.
Well, yeah, I'm going to give you an example here to show why they spread this out here. Yes.
So the only way to divide the matrix system by square matrices, you can never get it multiplied like non-square matrices.
I think I'm gonna pick on me if I don't answer your question in a moment, because I think I've got an example that might speak to that. And I'm gonna address this a little bit in a bit, because a transpose being invertible is the same thing. So if a matrix is invertible, its transpose is invertible. So here's the example. This is why you have to be a little careful. Suppose that I have this matrix here. Let's let A equal that and B now, of course, A is and B is 3 by 2. Right? And so actually I can multiply these two matrices in both directions, right? But they just give me different outputs, right? So if I multiply A times B, I'll get a 2 by 2. And if I do it the other way, I'll get a 2 by 3. Let's see what happens. This is a 2 by 2, and I get 1, 0, 0, 1. And you might say, well, goodness, Jim, look at that. Doesn't that mean that A is invertible? Well, no, because remember, you have to assume it's a square matrix in the first place. And actually, you're going to see what that is. Notice that A and B is invertible, right? But it's of a different size than both A and B. Now watch what happens when we go in the other direction. In the other direction, do BA. This is now going to be a 3 by 3 matrix. 1, 0, 0, 0, 1, 0, 0, 0, 0. Now, when you multiply in the other direction, you get 3 by 3 matrix. This one is invertible because it's short of pivot. Right? Like, okay, did that address?
Yes.
Okay. So another way, as I have pointed out, another way to think of this is in terms of linear transformation. So I'm going to speak to that a little bit now. So So. Okay, so what linear transformation was, if you remember, is it was a function from Rn to Rn to Rm. Now here I've got Rn to Rn because I'm assuming for now square matrix. But what it does is if you input some vector v, the linear transformation gets you a new vector over here. So if this is v, and this is linear transformation here, this would be T. Right? And like I said, we can usually realize this, or we can always really realize this as a matrix multiplication. What is an inverse? What happens when you multiply a matrix by its inverse? You get the identity, right? And what does the identity transformation do? It leaves everything alone, right? The identity. Put in a vector, multiply by the identity matrix, and you get the same. So there is a transformation. You can go back here. So what happens when you do T and then S, these two linear transformations? What happens when you compose them? Well, ostensibly what you get, if you get S of T of V, well, this is S of the matrix AB. And what does S do to its input? Well, it takes its input and it multiplies by A inverse. So what the inverse matrix does, if you think about this as linear transformations, is it's like an inverse function. You put something in, you do your function, you take your inverse function, it gets you back. It's sort of like you all remember inverse functions, right? How do you invert the exponential? You use the natural logarithm. How do you invert sine of x in the appropriate domain? You use the inverse sine, right? And this is the same thing going on here. So let me formally kind of write this down. Suppose T when Rn in the linear transformation. So I'm putting this in the language of linear transformations because that's what we're focusing on right now. But you all have probably seen this maybe in calculus or even pre-calculus in terms of functions and functions. And it's the same idea. T is invertible. So what do I mean for I've talked about what it means for the matrix to be invertible. What do I mean for the transformation to be invertible? If there is a linear transformation and Rn also. Such that S composed of T of X is X for all X in Rn and T of S of X is equal to X for all X in Rn. And this is actually kind of illustrates an important thing here. Lots of times, I think people first look at this and say, well, Jim, aren't you just like really in this overkill? Once you know that S of T of X is X, doesn't that mean that T of S of X is X? Not necessarily, because, for example, actually, it'll be good enough if you're going from Rn to Rn, but T going from R2 to R3 by oh. Is and let's say S goes from R3 to R2 by S of X equals A plus A is 0.0. Now, this should look familiar because I've just stolen it from the previous example, right? If you look at, which one do I want to do first? Yes. If you look at T, then what this is this is S of T of XY, which is S of, let's see, what's C multiplication by B. So this is S of X, Y, Z. If you multiply the spectrum out. And what does S do? S is multiplication by A. So it's 1, 0, 0, 0, 1, 0 times X, Y, 0, which is the vector. So notice your input XY, your output XY, right? What happens? Anybody will guess what happens if I run it the other way? What happens if I do TS? Well, if I do it the other way, my X is now S actually goes from R3 to R2. So my input is a three-dimensional vector. X, Y, Z. So this is T. S was multiplication by A. So this is T of the vector x, y, well, x, y, there we go. And now T is multiplication by that other matrix B. So this is 1, 0, 0, 1, 0, 0 times x, y, which is the free vector x, y, 0. Notice that basically what happened is doing it this way, you don't get the same thing because it turned that bottom z into a 0. But notice that the example, this is a little bit of a cheat example, because my linear transformations here, I'm going from Rn to Rn, right? I changed dimensions. Okay, let me give you this theorem. Let T from Rn and Rn. Again, both ends be a linear transformation. The standard matrix. So that is to say, I can represent a linear transformation by multiplication by that. Then T is invertible. Invertible. If and only if A is invertible. And this, I think, this theorem is exactly what you would hope for. The transformation is invertible if and only if the square matrix that represents A is invertible. And in this case, that is, if A is invertible, then T inverse X, that is the inverse transformation, is represented by A inverse. Okay, any questions? Okay, we got like a couple minutes left. I'm going to show you. Yes.
So with the like linear transformations and also with multiplying, so whenever you're trying to show that you can't get the identity matrix for multiplying two things like both ways. From like a 2x3 or 2x3 and like a 3x2.
Yeah.
But for like they both contain at least like 2 rows. So you're able to get like a 2x2 matrix that was like an identity.
Mhm.
Is it like safe to say that that's always the case that you can always get it from like a smaller dimension?
Yeah, that's right. If you go to, you do that to smaller dimension, if you have the appropriate, it depends on how many linearly independent rows.
Yeah, because this is like the transformations. If you're going from like 2 to 3 to 2, there's no like lossy thing there. So
That's right. Yeah, like when you're going up in dimension, it's too big. Yeah, we're going to see why that's true later. You might remember how we do this. Let's say, yeah.
Isn't it B? B. Is it B to the inverse? Inverse B, inverse A? Oh,
The way you do it, okay, it's just a transpose. All right. So suppose A is vertical. So A inverse, oops, is equal to the identity. Then by identity. Let me ask you all this. What is the transpose of the identity matrix? It is the identity matrix, right? Because you just get those zeros down the diagonal and you're just flopping the zeros back, right? So if you take A inverse transpose, this is the identity transpose, right? But the identity transpose is the identity. And this is A inverse transpose times A transpose. Right here. And notice that we can do this in the other order. A inverse A transpose is the identity. Transpose, which is the identity, which is now A transpose, A inverse. So guess what? A transpose is invertible if A is, right? And there's its inverse. Because you multiply that sucker by AT on either side and you get the identity. And this also shows that this thing is the inverse of A transpose. Because I know that when inverses exist, there can be. Any questions on that? Questions? All right, let me remind you that you have a quiz due today at 5 o'clock. I will, after class sometime, I will publish the next one, which will be due Tuesday at 5. Think about the math club, and y'all have a great weekend.